Hello, my name is Grace Jeruto, admission number TED 34/19. Welcome to my presentation of TEP 400. This section is divided into two, that is computer section and area of specialization, that is building and construction option. In computer section, there is two areas, that is SCADA. SCADA in full means supervisory control and data acquisition, and the Internet of Things. Let's begin with SCADA. SCADA stands for Supervisory Control and Data Acquisition, which is a software system used to control, monitor, analyze an industrial process. SCADA is a key software element in critical infrastructure control, and it is not a specific technology or protocol, but an application where data is collected from a system control that is a system. SCADA is a wide area network control system for diverse control assets that need to work together, such as oil and gas pipelines, water distribution system, and electricity transmission system. The history of SCADA system grew up from the telemetry systems developed for a space program, and the modern SCADA was born with a development of microprocessor and integrated circuits. The architecture of SCADA is control system that uses computers, network data communications, and graphical user interface for a higher level process supervision management. The two important elements involved in modern SCADA are the RTU and the central station computer. The SCADA system communicates in a real time with a controller out in a field that is running the actual process. The SCADA system also includes an historian that is so real time process information can be tracked over a long time. SCADA system have four main functions. Number one, we have data acquisition, data communication, data presentation, and data control. The communication network that connects the SCADA master unit to RTUs is in the field. Remote telemetry units. Servers are local connection points of gathering reports from sensors and delivering commands to control relays. SCADA systems are used control and monitor physical process, for example, which are the transmission of electricity, transmission of gas and oil pipelines, water distribution, traffic lights, and other systems used as the basic of modern society. SCADA systems in the electricity utility industry are the very foundation of the smart grid and many infrastructure operations. SCADA system also used in food processing, water and sewage utilities and manufacturing. Let's now go to the Industrial Internet of Things. The Industrial Internet of Things, that is IIoT, it uses the smart sensors and the real-time analytics to capture and analyze data in an industrial setting, allowing companies to save time and money, improve efficiency, and make a faster and more accurate business decision. Connected sensors and actuators enable companies to identify efficiency and process even problems earlier, improving process such as a predictive maintenance, field service, energy management, and assets tracking. Internet of Things is a network of intelligent devices that monitor, collect, and exchange and analyze with an edge device and an intelligent assets transmission of the information directly to the data and communication in the infrastructure of conversation in the action information. Cloud adoption is increasing rapidly, and it reduces operation costs, improving scalability, speeds up the app deployment, and increase reliability. However, the traditional cloud computing has some drawbacks for the IIoT, which include data security threats, performance issue, and rising operational cost. Therefore, it is important to collect and process data in a way that adds content and provide complete and accurate picture, and have a fast network and a wide broadband to handle increasing volumes of data in the future. Constructing data networks and systems also requires throwbacks away unnecessary data, avoid overwhelming the systems and incurring in an increasing cost. IIoT has the potential of revolutionization manufacturing and industrial process, but carefully planning and implementation is necessary to ensure its success. This other section is the area of specialization. I'm going to begin with cement manufacturing. The process of manufacturing cement starts from the quarry, where the raw materials like the limestone and clay are extracted through blasting. The extracted rocks are crushed into small pieces and set to the cement plant on the conveyor belt. The raw materials are pre-organized in the clay blending beds to reduce the chemical fluctuation, and then the fine powder is obtained from the grinding, is mixed in an emergency silo to get the consistent chemical composition. The blended raw meals is then heated up to 850 degrees in a preheater tower using the exhaust heat of kiln. The preheated meal then goes through the series of silos in the tower, and then the hot gas from the kiln, it is by the heat transfer reduces the carbon dioxide footprint. The blended meals in the sintered up to 1450 degrees is rotally clean with a flame produced by a high technology burner nose, and the fuels used can be fossil-like or renewable fuels like biogas. The resulting cleaner is cooled down to the approximately 100 degrees, and the ground with the gypsum and other natural or recycled constituents like the limestones and slag to produce the cement. The cement is then stored in silos, and the quality control checks are performed regularly to maintain the consistency in composition and performance. Finally, the cement is packed and shipped in a bulk or bags through various modes of transportation. The process aims to minimize the waste and reduce environmental impacts, and rehabilitation plans of each quarry includes promotion of local biodiversity. Our second part is Proctor tests. The standard Proctor test is a method used to determine the maximum dry density and optimum water content of soil. The dry density of soil for a given compactive effort depends on the amount of water the soil contains during the compaction. The test requires materials such as compaction rammer, mold, assembly brush, rubber mallet, trowel, wrench, straight edge, tool, and spray bottle. To begin with, the soil sample is placed through a number of sieves, 4 sieves, and water is added to prepare 4 specimens with water contents and bracket the estimates at optimum water content. The specimen is then compacted with a rammer, and the process is repeated for 3 layers with soil for greater moisture content. Also, after compaction of the last layer, the collar and the base plates are removed from the molds. The mass of the specimen is determined and recorded, and a specimen of water contents obtained. The dry unit weight and the water content of each compacted specimen are then calculated and the compaction curve is drawn. The optimum water content and maximum dry unit weight are determined. The compaction curve of the soil sample follows a parabolic behavior which falls under the sandy self-bell shaped category. This is the end of my video and thank you for watching.